So we'll give a couple more minutes before we get started. I already saw somebody had raised their hand. I believe the right way to ask questions is to pose a question in the Q&A. And I'll keep an eye on that. And I think the chat may be a little bit more busy. So Eneko, if you can keep an eye on that and let me know in case there's any issue with audio or whatever, just keep me posted. But I'll otherwise pay attention to the Q&A. So if it's a question for me, please ask it in the Q&A. And if it's a question in terms of logistics, maybe it's better posed in chat and Eneko can pay attention to that. And so while we are waiting, there's also a poll question that I don't think I've initiated. I'll initiate it right now. And the question is also on my next slide. So while we're waiting, if you can just answer this question, I think it'll help me kind of tune my discussion to all of your backgrounds. I'm really happy to see that the poll results are similar to what I had expected. So this is great. I don't have to deviate too much from what I had planned, so that's good. Okay, so hopefully I think we've captured a representative sample. So I'll just end polling and maybe share the results with you all. And so you should be able to see it, I think if you click on polling. Okay, so I think let's maybe get started. I'll just answer the other logistical question about whether the slides are going to be shared. I believe the slides are already online. And so if you're a registered attendee, I believe you have access to a portal that should have the slides right there. So yeah, so the slides are going to be available. Okay, so let's maybe get started now. And let me first, of course, start by introducing myself, and and firstly welcome all to what I believe is the very first session in this summer school. And I'm going to be talking about machine learning accelerators, and maybe more precisely, deep neural network accelerators. I'm Rajeev Balasubramonian. I've been a faculty member at the University of Utah since 2003. And over the years, I have explored different aspects of computer architecture. So I kind of began my career looking at cache hierarchies. I then moved into memory systems. And then from memory systems, I kind of found a backdoor entry into this world of accelerators. And in the last 5 or 6 years, I've been focusing on accelerators for both machine learning as well as for genomics. And so, so when Koen kind of asked me to do this the summer school, I offered to either do it on memory security or machine learning accelerators. I figured this one would get more attendees, and that certainly seems to be the case. I'd like this session to be as interactive as possible. So I teach a semester-long course on this topic at Utah. And what I've tried to do over here is kind of condense an entire semester's worth of content into 3 different sessions. That's kind of, this is at the bottom of the slide, you can see how I've organized it as Monday, Tuesday, Wednesday. So today I'll be focusing on the basics of how CNNs work and how accelerators work. And I'll kind of do it by just introducing you to some commercial designs. And then, maybe from there we'll jump into some discussion, and then I'll kind of get into some more nitty-gritty details and what recent papers are trying to do, what the next wave of innovations might be. And so we'll save that for Tuesday and Wednesday, right? So today I'll kind of try to focus a little bit on the basics and keep the content somewhat light. Like you've seen from the poll, it seems like most of you are in these top 2 categories up here. And that's kind of how I've organized it, right? So this is, I'm going to assume that you don't know a lot. I'll try not to spend too much time on the basics of CNNs. I realize some of you already know that. And so I'll try not to bore those of you that already understand CNNs to some extent. But, I'll kind of cover it fast, pause for questions, and then we can dive deeper based on your questions. Okay, I'll save discussion of innovations and recent papers for Tuesday and Wednesday for the most part. All right, and so like I said, just again in terms of logistics, please feel free to ask questions. If it's a logistical issue, you should maybe post that in chat. If it's a question that, if it's a technical question that you want me to answer live, you should pose it in the Q&A. And I'll take a pause every few slides to kind of look at the Q&A questions and try to answer them. I think by default, your questions are not shared with everyone, but I think once I click on it, you'll all be able to see the questions. Okay, all right. So with that, let's kind of get started. I'm also going to assume that not everybody is like a computer architect. I realize the summer school has a pretty broad emphasis, right? So let me just kind of start with some basics on computer architecture, and why accelerators have become this really hot topic. And so if you look at the history of computer architecture, right, there's we all know about Moore's law and how transistors have doubled every 18 to 24 months, and computer architects for the most part have figured out how to put those transistors to good use. In recent years, of course, there have been certain challenges, right? So one is single and multi-core performance has not been improving a whole lot. Part of the reason for that is that we're coming towards the end of scaling. We are also suffering from the end of Dennard scaling, which says that the voltage can't drop at the same rate as the transistor is shrinking, right? And as a result, we can't be increasing frequencies without kind of hitting into a power wall, right? And so because of these various issues, we are entering the era of what is called dark silicon, which means that part of the silicon area cannot be active. At all times there'll be some region on the chip which has to be kind of shut off. Or you can do dim silicon, which says that the whole chip can be active, but they should all be running at lower than peak frequency, right? And so as a result, chip vendors like Intel, IBM, AMD, and so on, they're essentially realizing that since not all parts of the chip can be turned on, maybe there are certain regions of the chip that can be designed for specific purposes, essentially putting accelerators into the chip. And that way, depending on the workload that you're running, there are certain parts of the chip that can be turned on and other parts that can be turned off, right? So in some sense, accelerators are compatible with this notion of dark silicon. Another reason to pursue accelerators is the fact that it's just getting much harder to make single thread and multi-thread cores run much faster, right? So we know about out-of-hour execution, we know about speculation, all of that has helped improve performance quite significantly. But if you want to take the next big jump, it takes a large amount of complexity, a large amount of extra power to get that next big jump, right? And so we've kind of picked the low-hanging fruit. There's no easy idea that can help us elevate performance a whole lot. Whereas with accelerators, there's a lot more scope because it's not as it's not quite been embraced commercially yet. Okay, and so the other aspect with accelerators is that if a company puts in the investment to place an accelerator on the chip, The hope is that there'll be somebody using it all the time, right? If an accelerator is just sitting there idle for the most part, it's not really a good investment, right? And so you need workloads that are going to be, on all the time. And until now, those workloads have not quite existed. But thanks to the emergence of deep neural networks in the last few years, we are perhaps at a point where there are these workloads that everyone is going to be wanting to run all the time. And so dedicating some silicon real estate to that can have a huge benefit. Okay, and so I just wanted to make sure that people were aware, why accelerators have become this hot topic in the last few years, right? So deep neural networks have taken off. We are hitting certain walls in terms of general purpose processor design. And so accelerators are kind of compatible with the way both hardware and applications are headed. Okay, any questions? It's still early days, and so you don't feel compelled to ask a question just yet. But I'll kind of pause for a minute after every slide or two just to see if people have questions. So some of you have noticed are raising your hand. I don't think I can give you an option to speak. So I think the way to do this is to pose a question in the Q&A, and then I'll try to get to it. Okay. All right, so here's I hope I didn't, yeah. So here's a slide that Olivier Temam had posed when he gave his keynote at ISCA 2010, right? So he was kind of a little ahead of his time. This is, back in 2010, nobody else was really looking at accelerators and neural networks. And I think he was visionary enough to realize that this new trend was on its way. And so he essentially showed this hype curve. And some of you might have seen the more traditional Gartner hype curve. It kind of looks like this, where when a new topic comes along and there's a lot of excitement in it, there's a huge jump in excitement, right? And so the y-axis is basically hype or activity in a certain area, and so it kind of really goes up. And then because of that hype, the expectations are pretty high, and inevitably that new technology fails to live up to those expectations, and so suddenly people start to lose interest, and that's what causes this drop in activity and excitement. And then after that, you enter what is called the plateau of productivity, where there's a lot of where expectations are firstly tempered down, and there's a lot of effort that actually advances the field and makes solid progress, right? So that's kind of the typical hype curve. With neural networks, it's gone through multiple of these crests, right? So back in the 50s and 60s, when neural networks were first invented, there was a lot of excitement about its potential. Then it kind of dropped. Then multi-layer perceptrons came along. That led to even more excitement. And then there were some results that basically showed that a single hidden layer is enough to model any kind of function. And so people were kind of misled into trying to were misled into trying to develop networks that had only a single hidden layer, and they were unable to kind of achieve very, very good results with that. And at the same time, there were other competing technologies like support vector machines, and because of that, that led to another drop in excitement. And then when he says today, that's 2010, right? And I think this curve has continued its upward ascent. And this is kind of also scary. Are we near the next crest? And my take on this is that deep neural networks and hardware for deep neural networks are here to stay, right? And so, if I look back at this in 10 years, I may think differently. But at least for the near future, it seems like this is a topic that's almost become the new baseline. All right, so there's a question about, can we say the GPU is an accelerator? And the answer is absolutely yes, right? And so, so GPUs were designed as an accelerator for graphics workloads. And then people then found a way to use that same hardware for other purposes. And that led to the era of what is called GPU, general purpose GPUs, where it was used for all kinds of scientific workloads. And then, of course, in the last many years, it's been used primarily for training of deep neural networks and even for inference of deep neural networks, right? And so kind of, and even GPUs are now evolving to be kind of, more tailored for deep neural networks. So GPUs are certainly the first example that you would say in terms of accelerators. Yeah, we are now entering this next wave of accelerators that are especially customized for deep networks. All right, so let's so like I said, this hype is certainly continuing, and one of the reasons that we kind of not hit that downward crest is because industry has also realized that there are huge benefits to designing these hardware accelerators. And so there are examples of these chips coming from so many different companies. And in fact, the recent MLPerf paper talks about 100 different companies trying to build chips for machine learning inference, right? And obviously I can't fit all of those 100 logos onto the slide. So this is only a sampling of some of the major companies that are that are pioneers in this field, right? And so in the second half of today's lecture, I'll go through summaries of what some of these chips actually look like. Okay. Again, I was just taking a brief break to look at questions. So please kind of share questions. At some point, I may not answer every question if it kind of makes me go back to an earlier slide or is a slight detour. But at some point, maybe during the break in the middle of the lecture, I'll come back and look at some of these questions. Okay, and so, it's also worth noting that this is not the first time that industry has also built neural network chips. So, back in the 90s as well, there were a number of companies that actually designed chips that were customized for neural networks. And that didn't pan out because of the reasons that I list over here, right? So like we saw earlier, support vector machines were doing pretty good. It also turned out that general purpose processors were getting much better. So you could invest all this time and effort to design an ASIC, which is a custom chip. And it would just turn out that the next general purpose processor that you designed was better at that same workload, right? And also there was a limited market for machine learning. And so none of these factors apply today, right? So today there's a big market for machine learning and for deep neural networks. There is no competing technology out there that is threatening to overtake these artificial neural networks. And general purpose processors are not getting that much faster, right? And so, that's another reason why we believe that upward trend is going to persist. Okay, so here's kind of the outline of today's discussion. I'm going to start by just introducing you to deep neural networks and what they look like. And then I'll kind of spend the second half looking at a number of examples from industry. And we can maybe try to understand what are the common features in this, and is there any secret sauce that allows these chips to be much faster at executing deep neural networks. Okay, and just as a preface, I just wanted to mention that there are many, this is a very broad area. And I'm not going to touch on all of them today, but hopefully over the course of these 3 lectures, I'll touch on many of these aspects, right? And so some of the major axes along which you'll see different designs is firstly, is this a chip being designed for deep network inference or for deep network training? And today I'll focus mostly on inference, but in the third lecture, I'll spend some time on training as well. Another aspect is, are these artificial neural networks or are these spiking neural networks, right? And so there are different ways of designing these neural networks. And for the most part, most literature today focuses on artificial neural networks, right? That's where machine learning has taken giant strides. And the spiking network area has received less attention and has taken smaller strides. But we'll spend some time on that as well on Wednesday. These chips that we are kind of going to design, or that I'm going to discuss the design of, could either be employed in a data center, right? And so if you're doing training, that usually happens in a data center, where you have much higher power budgets, much higher cooling budgets, and so on. And in those cases, you would design a much bigger chip that's perhaps focused on throughput. At the other end of the spectrum, you may have chips that go into edge devices like your phone, right? Or maybe just sensors in the wild. And those devices have much lower power budgets, right? And so in those cases, you might want to design a chip that consumes less than a watt, right? And so in some sense, we can design for different markets and different domains. But some of the principles that I'm going to discuss in these 3 lectures will apply to both of these. Another major differentiating factor is, when we talk about deep neural networks, they've primarily been used for 2 major applications. One is for image analysis, either image classification or object detection. And then the second major class is for language, right? So maybe text to text conversion, right? Either translation or speech recognition and so on. And the networks that you would use for these 2 are also very different, right? And so that's why it's kind of worth understanding what the differences are in each of these. Okay, so let me just pause for a second, see if there are questions I should answer before moving on. Yeah, so some really good questions here, but some of them may take me over. It may end up being a detour, and I think I might answer some of these as we progress. So let me just hold off on some of these questions, but please don't feel shy in terms of asking questions. If I don't get to many of these, I could also spend some time, having some prepared responses, maybe at the next lecture, right? And so I'll try to do a few of them in the break today. There are a few of them that I'll answer as I go through my remaining slides, and then I'll maybe save some for the next lecture. So please don't hesitate to ask more questions as we move along. All right, so let's just kind of start with the basics. Again, many of you already know this, so I won't spend a whole lot of time on this. But the basis for deep neural networks is, of course, the perceptron or the single artificial neuron, which I'm showing you on this slide over here, right? Where you have 3 different inputs in this example, x1, x2, x3. And to do any computation, what you do is a linear combination of these inputs. So the neuron has some weights that have already been determined beforehand, W1, W2, W3. And so all you do is this dot product, which is x1 times W1 plus x2 times W2 plus x3 times W3. You add a bias, and that essentially kind of tells you the output of the neuron. Okay, now it turns out that the neuron gets its power by applying an activation function to this dot product, right? So that's kind of this so this f over here is the activation function, right? And this activation function essentially smooths out the output, while also making it a step function. And so there are many examples of these activation functions like sigmoid, tanh. ReLU is kind of widely viewed as the state of the art today. And so what ReLU does is it basically says that, so if this is the input to the function, and this is the output to the function, it basically says that if the input is negative, the output is just 0. And if the input is positive, the output is nothing but the input itself, right? So this is the shape of the ReLU curve, right? So if this calculation gives you a number, let's say minus 0.3, the neuron output is nothing but 0. Whereas if that calculation turns out to be plus 0.1, then the output of this neuron is going to be 0.1. Okay, so ReLU turns out to be kind of one of the most effective activation functions. And it's also easy to implement in hardware because all it is converting negative values into 0. Now, it's worth noting that the activation function is really important because let's say that you're designing a multi-layer neural network, right? If you didn't have an activation function, you could basically condense all of this to say that, if each neuron is nothing but a linear combination of its inputs, you can convert all of this into a single layer neuron where the output is nothing but a linear combination of its inputs, right? And so the real reason that these multi-layer perceptron networks work is because of the activation function. It takes what would be a linear function into a non-linear function, right? And so the activation function is really important in terms of giving neural networks the power that they have. Okay, so that figure that I drew at the very end is kind of similar to this figure over here, which is nothing but a multi-layer perceptron, right? And so people have basically said that let's add many layers to this network, and that should somehow be able to give us higher performance, right? And so the question is, why is this multi-layer network more effective? So many of you have probably taken like an undergraduate computer organization class where you may have learned about the carry look-ahead adder, right? And I'm giving you an analogy just to give you a sense for why these deep neural networks work, right? And so if you take a 32-bit adder, you can explain it with some kind of truth table, right? Saying here are the possible inputs, and then here are all the possible outputs. And that's going to be a really large truth table, right? If you're trying to do 32-bit addition, that's a really large truth. That's a really large truth table. And we know that once you have a truth table, you can convert it into a logic circuit that's made up of just 2 sequential layers of gates, right? Any truth table can be expressed as a sum of products Boolean equation or a product of sums, right? And that means that I can have like a number of AND gates followed by a number of OR gates, and that should work, right? And it turns out that if you design it that way, it becomes a very, very complicated circuit because every single gate has a very high fan in and fan out. right? So the way we kind of solve that problem, and in an undergraduate class, you may have seen that circuit, is we introduce these signals, right? We introduce signals called generate and propagate. And that makes the circuit a lot more modular, right? So we essentially say that for every collection of bits, let's produce a generate signal, let's produce a propagate signal, and then let's compose these circuits to build the eventual carry look ahead adder, right? And that gives us a sweet spot in the design because it allows us to come up with a result while going through a modest number of sequential gates. And each gate itself has a modest number of inputs and outputs, right? And so we kind of use this modularity to get a more efficient circuit. And I think the same concept applies to deep neural networks as well, right? If I had said, since one hidden layer can model any function, let me just use one hidden layer, right? That results in a very complicated network. And so instead what we say is let's decompose this into a many layer network where the first few layers try to figure out some simple features, and then we try to put those features together to detect more complex features in the later layers. Okay, so this is just kind of an intuitive feel for why a deep neural network is better than a shallow neural network. Okay, now it turned out that some of the early attempts at designing these deep neural networks were not very effective. And the reason for that was the vanishing gradient problem, which basically says that when you're trying to train a deep network, it's relatively easy to figure out the weights for the later layers. But by the time you propagate the weights to the early layers, they end up having a very slow speed of learning. So in this figure, I'm kind of showing you like a simple network with 4 hidden layers. And the green line over here, right? So this line over here shows you the speed of learning for the last layer, for the 4th layer. And you can see that the speed of learning for the first layer is orders of magnitude lower than that, right? And so this is known as the vanishing gradient problem. And I won't go into the math behind why that's the case. But essentially, as you're updating the weights for this last layer down here, you're going through a number of instances of sigma prime, right? So sigma is the sigmoid function, the activation function. And so, the differential of that plays a role as you back propagate. And so since that number is less than 1, the more layers that you have to navigate, the slower the speed of learning, right? And so the vanishing gradient problem is what made it hard to train these deep networks. And so it is only around 2005 and so on that people figured out some of the early techniques that allowed us to overcome this problem. Okay. Again, I'll just take a quick peek at questions and yeah, so there's a question about where does this model come from, this model of the neuron, right? And so in some sense, it was inspired by biology, but over time, they've kind of deviated from that initial biological model, right? So these deep neural networks are actually, so the neuron basic model is kind of like how the brain's neuron operates, but the artificial neural networks today are trained with something called stochastic gradient descent, which is a process of trying to minimize a mathematical cost function. The brain, of course, does not do that, right? So in some sense, while the initial neuron model is biologically inspired, we've kind of deviated from that in terms of the mechanisms used to train these neural networks. Okay, and I think we can have a deeper discussion about about being faithful to biology versus an artificial model when we talk about spiking neural networks on Wednesday. Okay, so let's carry on, right? So what are some of these techniques that made it possible to train these deep networks, right? So what I just said over here is that deep networks are hard to train because of vanishing gradients. So what can we do to overcome that problem? Okay, so one of the early innovations in the space was to introduce what are called convolutional neural networks, right? And so let me explain what that means. So let's say that you have a bunch of input values over here, right? So these are the inputs, and let's say that they happen to be the pixels of an image. So I'm giving you an input image, and each pixel value, is potentially different. And because it's an image, I'm organizing it as a 2-dimensional grid. Okay, but you can just imagine it as being like a linear set of inputs. So in the very first layer of the neural network, what I'm going to be doing over here is I'm only going to look at the first 25 neurons in this example, or the first 25 inputs. And I'm going to do the dot product over those 25 inputs. And that gives me an output neuron, right? And so that produces the result that I'm placing over here. Okay, so usually, or at least in this figure that I showed you over here, a single neuron over here takes, gets inputs from all of the inputs that are available, right? All of them feed into every single neuron. But I'm changing that model over here, right? What I'm instead doing is I'm saying that the first neuron that's going to produce a result is not going to look at all the inputs, but at a small window of inputs. And that's referred to as a local receptive field. So it's just receiving inputs from a small field, in this case, 25 neurons, which means it needs 25 weights, right, to do the dot product and then come up with the result of that neuron. Then the next thing it does is it's the next neuron, and I'm just going to amplify this figure a little bit. This next neuron gets inputs from the next 25 inputs, right? And so basically that the stencil that you're applying keeps shifting from left to right? So I'm kind of showing it over here, where everything is shifted one place to the right. And you do this until to figure out the results of each one of these neurons until you get to the very end. Then you shift that stencil one place below, and then you start working on these neurons and so on. Okay, so you'll see that that set of inputs has essentially has gone through one layer of neurons to produce this output over here, right? So this is referred to as an input feature map, and this is referred to as the output feature map. And you've done this transformation by saying, I'm going to take what is referred to as a filter. And this filter has 25 weights. So there are 25 weights, also referred to, and this is also referred to as a kernel. Right, so I've basically got the set of 25 weights. I'm applying it to the first 25 neurons to produce the first output neuron. Then I'm going to shift it one place, apply to a different set of inputs, get the next output neuron, and I keep repeating this. Okay, and so this is essentially the process of taking a convolutional filter and applying it to the entire image to produce a new output feature map. Okay, and so one of the reasons why this kind of helped the training process is because I've dramatically reduced the number of weights. Right? Not only is one neuron getting inputs from a limited set of the inputs, those same 25 weights are being shared by all the neurons, right? Whereas in this earlier strawman example, each of these neurons, if there are n inputs here, each neuron needed n different weights. And each one of these neurons in this layer needs a different set of weights, right? And so that meant that there was a large number of weights in this early layer, which would take a very large amount of time to train. All right, so what you instead done over here is to say that, let's not look at all the inputs, let's look at a limited field of inputs. And the weights that I use are the same weights that everybody in my layer is going to use. So layer one only needs to train and learn 25 different weights. And so that kind of helps overcome this vanishing gradient problem. Okay. Again, just taking a quick peek at the questions. Yeah, so in some sense, these slides are answering one of the questions that was posed, which is, how do CNNs overcome this problem? And that's by kind of having a small set of weights. Okay, so what I've just shown you over here is here is a set of inputs, right? So this is the input image. And let's say that it's a small input image with just 28 by 28 pixels, right? So 784 pixels over here. And what I did is I basically applied a 25 weight filter to produce this output feature map. Okay, now what I can also do is in parallel, I can apply a second filter over here. This is a second 25 weight filter. And I can apply it to the same input to produce a different output feature map. Right, and so that's what I'm showing you over here. So this is, this is a second output feature map. And in this example, you're seeing 3 arrows over here. So I've basically applied, 3 different filters to the same set of inputs to produce 3 different output feature maps. Right, so 3 filters gives me 3 output feature maps. Okay, and so let's kind of take a step back and look at what I'll get back to this slide in a second, but I was going to show you this input over here, right? So there was an input image. I applied 4 filters to produce 4 output feature maps. Okay, now I'm going to send these feature maps are now being sent through layer 2. Okay, and I'm going to apply filters to these inputs as well. Okay, but now note that what used to be a 2D image over here has just turned into a 3D image over here. And so the filter that I apply to that image is also going to be a 3-dimensional filter, right? So this is the filter that I'm going to be applying to that. So I apply the green filter to this set of 4 output feature maps, right? And so this is, let's say this could be 5 by 5 by 4, right? So there are 100 weights in this filter. And so I have to do a dot product involving 100 computations, apply the activation function that produces the first output neuron over here. Then I shift it one place to the right, it produces this output neuron, and I keep doing this whole process again. Right, and so I apply a 3-dimensional filter to the set of inputs to produce this output feature map. Sorry for the bad handwriting, I'll slow down. Then I apply the orange filter, just like I applied 4 different filters over here. And these are 2D filters. Here I'm applying 2 3D filters. I'm applying a green filter and an orange filter that produces all of these output feature maps. Sorry, these output neurons in that output feature map. Okay, makes sense, right? So the filter, is 2D if the input is just 2D. But if the input is 3D, which is the case for most layers, then the filter also becomes a 3-dimensional filter. And you go through the same process to produce multiple output feature maps. Okay, so let me just again pause to just see if there are questions that I can quickly answer. Okay, so I've not answered too many questions. So I'm just going to save them for later. I'm just kind of trying to answer the questions that pertain to something I may have just explained, but I'll try to get to some of these questions later. All right, so let me just again take a step back, right? So what is the filter trying to do, right? The filter is kind of looking for certain patterns. So, one exercise that I would recommend that you do is, let's take a filter that looks like this. So let's take a filter where the weights are 1, 1, 1, 1, 1, and everything else is a 0. Okay, and so, take an input set of pixels, apply the filter to that and see what output result you get. And you'll see that the output is pretty high if the input image also kind of looks like this, right? So in some sense, the filter looks like the pattern that it is looking for. So if this is what the filter looks like, what it is really doing is it's trying to see, do I find something that looks like a diagonal line, going from the northeast corner to the southwest corner. Okay, so a filter is essentially, it looks like the pattern that it is trying to discover. And so a high value over here means that I found something that looks like this over here. A 0 value over here means that, the shape over there looks completely different, right? And a 1 over here means that, yes, again, I found a line like that over here, right? And so that's the meaning of a feature map, right? So this filter is defining a certain feature. And this is basically a feature map saying that, if you see a 0, that particular feature does not exist in that image. If you see a 1, that feature exists, right? And that's why this is called a feature map. It basically says that if the feature defined by this filter, here's where you can find it in the image, and here's where you can't find it in the image. Okay, so in some sense, when I apply 3 different filters over here, this one could be a diagonal line detector. This could be a circle detector, right? And all kinds of things, right? And so you can kind of see the inside behind these deep networks, right? The early layers are essentially saying, at first, let me look at small regions of the image. Let me see if I can find a diagonal line or a straight vertical line or a horizontal line or a circle or a curve, whatever, right? And I want to do all of this in parallel. So I apply a bunch of parallel filters to that initial image, and I produce a whole bunch of feature maps that help me figure out, where can I find all the vertical lines, where can I find, the diagonal lines, and so on. And then in later layers, I'm going to take these simple features and piece them together, right? And so if I'm looking for a face, I should know that, there should be a circle in this general region. There should be, eyebrows in this general region. and so on. So that's kind of the insight behind these deep networks, where the early layers are looking for some localized features, and the later layers are trying to put those localized features together to discover, more complicated features. Okay, now, while that was a very intuitive explanation, I kind of made it seem like the early filters are looking for specific shapes. That's not actually what happens, right? So the actual filters look something like this, right? So you can't really see a diagonal line or a vertical line or a circle over here. And it turns out that these filters are not being defined by humans. They're actually being learned by the training process, right? So you feed millions of images to the training algorithm, and it tries to figure out what the 25 weights or what the 25 weights in each of those filters is going to look like, right? And so, empirically, it just turns out that this is what the filters look like. So they're not, as well defined as I kind of made it seem to be over here. Okay, so these have to be learned, and they end up taking these weird shapes. Okay, so all right, let's. So we've so I didn't actually talk about these pooling units over here, right? So having gone through one of these filters, right? So I just explained what this process is. Having done that, we go through this next process, which in this example is a pooling layer, which says that I'm trying to kind of condense all of this information, right? So I kind of know what, the 4 values of a feature map, but I want to make this image smaller. And so I can take those 4 values and, condense them into either a max value, which then becomes this output neuron over here, or I can take the average of those values, right? So there are many different ways of doing the pooling. And the pooling is essentially trying to condense information from many pixels into a smaller number of pixels. So as the image goes through the deep network, it keeps kind of getting smaller and smaller from left to right. Okay, so getting back to this example again, right? So I had like a 2-dimensional image at first. I had 4 2D filters that got applied to it to produce these 4 output feature maps. Then I had 2 3-dimensional filters I applied to get these 2 output feature maps. Then I applied some pooling to kind of shrink their sizes down here. And then, and I can do this many times, and I'm just not showing it in the slide over here. But eventually you come down to some fairly small images, which have, where you've been able to discover certain complex features in that image. And now you're going to send it through what are called fully connected layers. Right? So these fully connected layers are basically saying that, you've produced all of these features. Now let me feed them, let's feed all of these features to all the neurons in the next layer, maybe have a couple of these layers, where, all the inputs go to all the neurons. And then in the very last stage, you're basically producing your outputs, right? So your outputs come out from here, where, if you're trying to detect, 1 of 10 different objects, you may have 10 different neurons, right? And the neuron that has the highest signal, that's the object that you have perhaps detected over here. Okay, so that's kind of my introduction to deep neural networks, and maybe it took a little longer than I wanted to, but I'll try to speed things up a little bit now, or I'll see if you have questions and we can dive deeper in specific parts. Okay, so here is kind of the secret sauce. That is, somebody had asked a question earlier, how did we overcome the vanishing gradient problem? And so this slide in some sense captures why we made these big strides from 2005 to 2015, right? So the first thing we did is we said, let's introduce these convolutional layers. So in the early layers, you have very few weights because you're only looking at a part of the input, and they are shared among all the neurons. And so there are only a few weights that have to be learned. A second thing that really helped is that we had access to GPUs, which made training much, much faster. We also had access to very large data sets, which were labeled. Again, you need to see a large number of inputs so that you can kind of fine tune the weights and make them more accurate, right? And with GPUs, we were able to do this in a matter of a few weeks. And that also led to these huge improvements. And starting with those initial big jumps, there were several other smaller things that were introduced. And so there are better activation functions. There are things like dropout, which basically says that these neural networks tend to overfit. And you can alleviate that effect by injecting noise during the training process, and that leads to better accuracy. There are also new techniques, things like initializing the weights appropriately, things like regularization, which improve the convergence of the training algorithm. There are also ways to take the input data set and kind of shift them in various ways to expand the inputs. So there are all kinds of many different tricks that were introduced. And so on this next slide, I've just tried to kind of capture some of the common terms that you'll encounter. And I'll just, I won't go through all this. I'll just flash this for the next minute as I kind of look at the questions and see if there are things I should answer at this point. So somebody asked if we lose data in the pooling operations, and the answer is, yes. So it is a way of lowering resolution as you go through the network. And while that might seem like a bad thing, it also means that the next layer has fewer weights that it has to learn, right? So it actually improves accuracy to lose information in some cases. The filters don't have to be designed manually, right? So the architecture of so somebody asked if the filters have to be designed manually each time. So it turns out that the architecture of the filters is something that is defined manually, and I'll kind of put an asterisk on that and explain that in a second. But you are the one who has to say that I would like to put it in a 3x3 filter, right? But the weights for those filters have to be figured out automatically by the training algorithm. Okay. Now there's also something known as neural architecture search, which says that even you having to define the 3x3 is not required. I will use let's say some genetic algorithms or reinforcement learning algorithms to figure out even what the filter size should be. Okay, so people are working hard to automate even that. Somebody asked if we are going to discuss processing in memory, and so that's something I'm going to discuss in the third lecture, right? So today is a little bit more focused on the basics, and so we'll discuss processing in memory in the third lecture. Let's see if there's anything else that. How do you select the initial filter set, right? So again, the initial weights are determined randomly, and through the training process, you ultimately converge on what the optimal set of weights should be. And in a similar way, somebody asked if random weight initialization is enough, and that's often, again, the case, yeah. Okay, so let me kind of stop with these questions for now, and let's kind of move on to the next topic, right? So we've kind of looked at the neural network architecture. Let me spend a couple of minutes on the data set as well. So the MNIST data set is the one that was very popular at first, and it's these 28 by 28 images, so that's the 784 pixels, and these are handwritten digits, and they were the kind of the workhorse of early deep learning, and then we've become so good at this that it's kind of almost become obsolete now, right? So today, if you use MNIST, you can expect a few raised eyebrows, right? So this has kind of become obsolete. It's only used if you're taking on a really challenging problem that no one has taken on before, or in terms of the learning algorithm, right? So today, for the most part, people use what is called Imagenet, which was popularized by this annual competition that ran for a few years. And so, millions of images, many categories, and usually about 1,000 categories that are used. And you're kind of testing it on what are called the top 1 and top 5 criterion, right? So you make your best guess of what's in the image, right? If that's correct, your top 1 accuracy improves, or alternatively, you make 5 guesses, and if the correct answer is among those 5 guesses, that increases your top 5 accuracy. Okay, now, more recently, there's also CocoNet, right? And so that's a new data set that is emerging as well. So, just be aware that these are the data sets that are being used. Okay, now here is the evolution of these deep neural networks over. Well, this is not a time graph, and I'll show that to you as well soon. But this is kind of this. So yeah, let me first explain the axes over here. So on the x-axis, you have the number of operations required to perform one inference, right? So this is not a graph that pertains to training. So the network has been trained. What we're looking at over here is trying to describe how many computations I have to do to take in an input image and then do a classification of what's the object that I find in this image, right? So on the x-axis, you can see that the networks on the right require more computations than the networks on the left. Okay, and you'll also see that the y-axis refers to the accuracy, And so the more computations that you do, in general, the higher the accuracy that you get as well. Right, and that kind of seems intuitive. And of course, there's a steep jump kind of over here, and then it kind of tapers off. Right, once you get to a certain accuracy, you can do a lot more computations. It only causes a small improvement in accuracy. The other thing that this graph is showing is the size of the model, right? So how many parameters do I have in this model, right? And so some of the biggest models over here have about 150 million parameters. Okay, and you'll see over here that, when people are looking at VGG, that's kind of where you had these large models. But since then, people have discovered things like ResNet and EfficientNet, and I'll talk about a few of these shortly. But a theme in all of those newer networks is that they've also been successful at reducing the size of the network, right? And so in general, if you make the size of the network smaller, it means you have fewer weights to learn. Again, that's effective at overcoming this vanishing gradient problem. And that actually makes it possible to train your networks to get even higher accuracy. Right, and so that's an important kind of take-home message from this, that not only are, yes, to get very high accuracy, you need to really increase the number of computations, but in many cases, you don't need to increase the size of the model, right? So the models in a lot of these cases are kind of hovering more in this range over here, right? So between 10 to 100 million parameters. And the good news over here is that these are sizes that a while back we said was, slightly bigger than the buffers that you can get on a chip. Today, we now have accelerators that have large enough buffers to accommodate all of these weights, right? So this is kind of, on the edge of being placed on a single chip. Right, and this has a huge, these has huge implications in terms of efficiency of executing these networks and in kind of making these accelerators very, very effective. Okay. So, so MLPerf is now kind of being viewed as a benchmark suite that's representative, and that's so when you come up with a new architecture, you have to test it out on different workloads. You don't have to test it out on every single workload, right? So the folks at MLPerf have done an analysis to show that testing your network or testing your architecture on some of these workloads is usually enough. Okay, and so you'll see over here that 4 of them are based on images and vision algorithms, so image classification and object detection, and then there's one that uses machine translation. And even over here, there's heavy and then there's light, right? So the assumption being that the light ones would execute on edge devices, on phones, and so on, whereas the heavy ones would execute in the data center. Okay, and you'll see that they basically use examples of ResNet and MobileNet, right? So you'll see that these are the ones that are kind of growing in popularity. Okay, let me just pause again to look at questions. Yeah, so there's a question about neural network accelerators for inference versus training, and in today's lecture, I'll just give you a brief overview of what those major differences are. But I'm going to save a discussion, a deeper discussion of training for Wednesday's lecture. Okay, all right, so let's, yeah, so here's the trend in terms of time, right? So like I said earlier, we are trying to make the models a little smaller, and that has a benefit in terms of the fewer the weights, the easier it is to learn those weights as well, right? And so that's kind of what we are headed towards. And so this kind of shows you that progression in terms of time, right? So it starts out with AlexNet, which was done in 2012, and it shows you that 7 years later, you can achieve the same accuracy as AlexNet with 44x less compute. Okay, so I apologize that the lettering on this slide is a little kind of dim, but it's kind of showing you the main points that have given the highest accuracies over time. And you'll see that because we've made the networks more efficient, because we've reduced the number of weights, it takes fewer computations to achieve that same level of accuracy right now. And of course, this is This is a nuanced discussion because we're not just trying to achieve the same accuracy as AlexNet. We're trying to go beyond it, right? And so there's clearly more to this puzzle, but I think it helps to understand that, I think this really drives home the point that the networks themselves are kind of becoming smaller, right? And this is compatible with what I mentioned over here, which is that we are kind of restricting ourselves to being in this range. And in some sense, the models are actually kind of getting smaller over time. And that's good news in terms of architecture design. Okay, so let's try to understand, what has helped make these models somewhat smaller. Okay, so let's kind of, there's a lot of content on the slide, so let me kind of do this gradually. So this figure is essentially showing the connectivity of various filters. Okay, so what I'd explained to you earlier is something that looks like this, which is a 3x3 convolution. Okay, so let me just kind of draw this out a little bit more. So here are my inputs. So these are my input feature maps. What I'm doing is a 3x3 kernel. And what I'd explained earlier is if there are 4 input feature maps, then a kernel is going to look like this. Right, so 3x3, and it has to be 4 deep. Right, so I essentially take this kernel and I apply it, place it over here. And that gives me the first dot over here, right? So it gives me the first neuron in my output feature map, right? And as I move this along, I get all of the other points in my output feature map. Okay, and now if I want to produce the second output feature map, I will need a second kernel that looks like this, right? So I take a second kernel, apply that, I'll get my second output feature map, right? So this is kind of how the filters work. Okay, what it means, and what I'm showing you over here is the spatial connection or dependency, and then the channel connection and dependency. Okay, so what that means over here is, let's take this output neuron over here. This is essentially saying that to get the value of this neuron over here, I need to look at a large set of inputs, right? I need to look at 9 pixels in this input feature map. Okay, because I'm doing a 3x3 kernel, so it means there are 9 input pixels that are all going to contribute to the output value over here. And that's what this is showing. It's basically saying it's not just me, it's my kind of 3 neighbors as well. Really speaking, it's 9 neighbors, but this is an illustrative figure, right? So it's kind of showing you that the value of the output neuron has a spatial connection. That means it depends on the 9 neighbors in that one input feature map. Okay, and so you'll see, and hence lots of connections, hence more weights that have to be learned as well. The second figure over here shows you the channel connections. It's basically saying that to get this value, it's not just these 9, it's also 9 pixels in this next input feature map, 9 pixels in this next input feature map, and 9 over here as well. So all of the input feature maps are contributing to this value being produced in this first output feature map, right? So a value in an output feature map depends on channel 1, channel 2, channel 3, all the way until 6. Okay, and so this particular filter that we have designed, right, which is what I introduced a few slides ago, has high spatial connections and high channel connections. And because of that, there are, in this example, there are 24 weights, sorry, not 3 times 3 times 4 is 36, right? So there are 36 weights that I have to learn. Right, and that's because there's high connectivity between channels and among pixels, right? And kind of 36 doesn't sound like a big number, but in practice the number of feature maps quickly becomes 64 and 128. So at that point the filters are pretty large, and similarly, if there are 64 such filters that I need to learn in each layer, that's many thousands of parameters that I have to learn, right? So 36 may not seem overwhelming, but in a realistic example, that number is many tens of thousands. Okay, and so that's the number of parameters that I want to kind of reduce, not just to improve accuracy and improve my learning speed, but also to reduce the computations that I have to do, right? And that's kind of what I'm trying to do as I go down from that initial baseline to these other primitives that I'm showing you on this slide. And it is these other primitives that now form the basis for all of the state-of-the-art networks like EfficientNet, ShuffleNet, and so on. Okay, so let's kind of try to understand what these alternative primitives are. So the first technique that we're going to look at is called grouped convolution, which says that, just as before, your spatial connections are going to be the same. So it's going to be a 3x3 kernel. Okay, but instead of making it 4 deep, I'm going to make it less deep, right? Instead of looking at all the input feature maps, I'm just going to look at a small group of input feature maps, right? And so in this example, I have, I'm showing you 6 input feature maps, and I'm breaking it up into 2 different groups, right? And so in the first group, I'm just going to look at feature maps 1, 2, and 3. The second group looks at input feature maps 4, 5, and 6. Okay, and so this reduces the number of connections that you can see, right? So so this input neuron, instead of getting inputs from 6 input feature maps, only gets inputs from 3 input feature maps. So it reduces the number of computations that I have to do by a factor of 2. Okay, so that's the grouped convolution approach. The next approach is referred to as depth-wise convolutions, which essentially says that, again, it's okay to look at a 3x3 kernel, but let's go to an extreme group size of just 1. Okay, so instead of the kernel, instead of being a 3-dimensional kernel, just becomes a 2-dimensional kernel, a 3x3 2-dimensional kernel. So that reduces the computations even more. The fourth one is called a point-wise convolution that says that, let's not look at a 3x3 neighborhood. Let's just look at 1 input pixel at a time, right? So you'll see that the connections over here have reduced. I'm just looking at 1 input pixel at a time and not looking at all of the surrounding stuff. Okay, and instead what I'm doing is I am going to look at that 1 pixel in all of the input feature maps. So if there are 4 input feature maps, I'm going to look at 1 pixel in each of the 4 input feature maps. That gives me my first pixel in the output feature map. Okay, so in some sense, it's basically saying that having discovered features in all, having discovered a wide array of features, let me condense all of that information into into 1 pixel, and that also significantly reduces the number of computations that you have to do, right? And so in the case of MobileNet, it's just a series of depth-wise and point-wise convolutions that happen, back to back to back. Okay, and this is also the case in some of these other networks, right? So ShuffleNet, for example, is basically group-wise convolutions, but you don't have the same set of groups all through the network, right? So after every layer, you kind of shuffle the groups. So it's a different set of input feature maps that form the next group for the next layer. Okay, but these are all approaches that say that, we started out with this baseline over here where there are lots of spatial and channel connections. Let me try to reduce that. That'll make things run faster. It'll also reduce the number of parameters. That should give me higher performance. Okay, so I was going to, I also wanted to give you a break after 1 hour. Maybe I'll do this next piece in the next couple of minutes. Then I'll give you all a short 5-minute break or so. And during the time, I can also go through the Q&A and try to answer some questions. Okay, so, in all of this discussion that I just had, we kept talking about images and pixels, right? So this is clearly focused on image classification. Let's just spend a couple of minutes on language as well, right? And so, in everything that we've seen so far, the neurons don't have any state. That means if I give you a new image, I don't remember what the previous image did, right? Based on the new image, based on the pixel values in this new image, you're going to do some calculations and you're going to produce some output feature maps, right? But with language, there's usually some context as well, right? Every time you see a new word, you have to also understand, what the other words were trying to say, so you can disambiguate things like pronouns and so on, right? And so there is some state that has to be preserved as you see, each next syllable or each next word. And so usually you want your neural networks to preserve some kind of state. Okay, and this is usually done with what are called recurrent neural networks, where you have all these neurons and the output kind of feeds back as an input in the next cycle, right? So when you're doing the next computation, the outputs you produced feed back as inputs, and that way you have some memory of what you have seen in the past. Okay, so LSTMs, or long short-term memory, are the most recent incarnation of these RNNs, and so this is kind of at a high level, this is what an LSTM network looks like, right? So it's just one network A, and what I'm showing you over here is it's processing in different time steps. And so in each time step, you're producing a certain output, and there's some certain state that you're kind of trying to remember for the next cycle. And so when you get your next input, right, so the next input kind of shows up over here. There is some state that you're remembering, and now you're going to do a whole bunch of computations based on that. Okay, so there's first a gate over here that says, I don't want to remember all of the state. Okay, so depending on what the input is, I'm going to hold on to some of that state and I'm going to get rid of some of that state. How do I make that decision? It's by going through this neural network over here. So this is nothing but a multi-layer perceptron, which says that given this input, let me make some best estimations of what state I should keep and what state I should discard, right? For example, if you see a period as your input, it's basically saying that, it's a new sentence, right? So maybe there's some context you want to keep, what is the topic being discussed? But a lot of the stuff can be thrown away, right? So that's kind of what you're trying to figure out in that first step. Then what you're going to do next is, out of this new information, how much should I actually retain, right? So the input itself comes in as a vector of bits, and how much of it should I retain? How do I make that decision? That's done with another MLP over here, right? So that MLP tells me, what I should keep and what I should discard. There's another MLP over here that says, what is the strength of the new information? How do I weight this input before I add it to the existing state, right? To produce a state that moves on to the next cycle. So there's all these decisions being made about, what state to produce, what output to produce. All of that is being done with these multi-layer perceptrons, right? So these speech processing networks are a little different. They're kind of trying to remember state that goes from one cycle to the next. And those decisions are often made with multi-layer perceptrons, not with convolutions. Okay, and so they look a lot like the second half of an image classification deep network, right? The first, when you're doing image classification, there's a bunch of convolutions at the start, ending in a fully connected layer. With speech processing, for the most part, is just fully connected layers. Okay, so now I was about to get into the second half of today's lecture, which is focused on commercial accelerators. But let me pause here. Let me give you all a 5-minute break, right? So this is where, we've discussed machine learning models. This is the workload that we're trying to optimize. And if people have questions, I'll start going through the Q&A now and start answering as many as I can. But you're welcome to take a break and come back in 5 minutes, and then we'll resume. Okay, and I'll try to answer some of these Q&As with text, and in some cases I'll try to answer them live. So there's a question about DNN's claim to solve dark silicon. So that's that's not quite what I meant. Right? So what I meant is accelerators are one way to add value to chips, right? So because of dark silicon, I can't keep the whole chip active all the time, right? But if my chip was a collection of different accelerators, let's say that there's a sorting accelerator and then there's a deep network accelerator, there's a small chance that I'm going to use both at the same time, right? And so in response to dark silicon, chip makers can put in an assortment of accelerators, and that's compatible with how workloads actually run, where they use some kernels some of the time and a different kernel the rest of the time. So a suite of accelerators, I think, is a good solution to the dark silicon problem, and deep networks just happen to be one of those accelerators. There's a question about does reinforcement learning affect accelerator architecture? So far, not significantly. I've not seen too many papers that do that. Part of it is because reinforcement learning requires fewer computations. And so it's, yes, an accelerator might help, but it's not a huge fraction of the total workload. Yeah, so a question about why is it called long short-term memory, right? So again, I'm really a computer architect. I'm just kind of pretending to be knowledgeable in machine learning, right? So I don't have a perfect answer for this, but you'll see that as you're kind of preserving state, I believe it is because there is some short-term memory of what you've just seen, right? So I believe that plays a role in that definition, but you should maybe Google might give you a better answer than I'm giving you right now. So yeah, so good question about are models getting smaller for NLP as well, right? And I have a colleague in NLP who I think would have a much better answer to that, and I'll maybe send him an email and see what he says. My initial guess would be that probably not, right? So one of the reasons that the image classification models have been getting smaller is because they rely on convolutions and these tricks I just showed you in how to reduce connectivity in these convolutions, right? And but the last fully connected layers I think tend to get bigger over time. So my my kind of my speculative answer over here is that NLP models are probably not getting smaller. Right now, at least in the NLP space, they're using things like transformers and attention. I have not understood those well enough to know if they can help reduce the model size, right? So attention is kind of like a way to figure out where the interesting parts are, and then that kind of feeds into all of the computations. And I don't know if that has helped make the model smaller. Yeah, so there's this question about, there are very regular structures. Why is it challenging to implement efficient accelerators, right? And I think that's a really good and deep question. And so we'll keep discussing this as we go through, right? And so by the end of today's discussion, you'll say, yeah, it's very easy for me to design an efficient accelerator. And to some extent, I would agree with you on that claim, right? And so I kind of feel that it's very easy to design a first generation accelerator. I think when you try to improve that and try to get a 10x improvement for the second generation accelerator, that's where I think things become a lot more tricky. And I think that's why you're seeing all this research activity in this space. So I think the first generation accelerator looks very straightforward, but I think it's the next generation that's a little harder. So there's a question about how are the elements on the border considered, right? And so you're essentially, so the output feature maps are usually smaller than the input feature maps because you try to apply the entire filter, right? So in the examples that I had earlier, I had a 5x5 filter, which meant that the 28x28 input feature map turned into a 24x24 output feature map. So you're still applying the full filter. It just means that you're not going to go all the way to the end, right? You apply the computation 24 times in a row, then you stop. So I think I've answered most of the recent questions, and I'll maybe get to some of the earlier ones later. Yeah, so somebody's also asked about what are the main challenges. And like I said, today we may not get through a lot of those challenges. I'm just going to do the basics. But I think by the end of the 3-lecture course, you'll have a better sense of what those challenges are. Okay, so let's resume again. And like I said, this is officially supposed to go on for 2 hours. And so at that point, I'll probably stop and I'll just take questions. And if there are some slides still left, I'll save that for the next lecture. So we have about 45 minutes more, and please keep continuing to ask questions. I'll stick around for half an hour after the session ends, and I'll try to answer as many of those questions as possible too. Okay, so let's carry on, right? So the first half was basics of what are the computations actually being done, right? So what do convolutions look like? What do fully connected layers look like? And now let's get to the actual chips themselves, right? So that's kind of the real topic of this course, which is how do I design hardware? How do I design accelerators? And like I said, more than 100 companies trying to design these chips for both inference and for training. And so I'm going to start by just throwing out a few examples, right? Let's look at what the Google TPU looks like. Let's look at what the Tesla FSD looks like, right? And so I'm going to do 4 or 5 of these architectures. And as we look at them, right, you'll see certain features, and based on your questions, I'll dive deeper and give you some justification for why those features exist. But you'll start seeing that there are some common features, and like somebody asked in the question, they look very straightforward, right? I mean, it's a very regular computation. We're just doing dot products all the time. So the compute unit should also look fairly straightforward, right? So is there any secret sauce over here? And I'll do some introduction today, but I'll save some of the more deeper discussion for Tuesday and Wednesday. Okay, so let's start by looking at the Google TPU, right? And so this was kind of what started excitement in this area, right? I mean, there were the papers in 2014 that introduced Dian now and Dardian now. They were the first kind of academic accelerator papers for deep learning. It won all the best paper awards in 2014. And I have a feeling that this area may not have survived for very long if industry didn't dive in as well, right? So thankfully for us, thankfully for most of us, industry decided to also invest heavily in neural network hardware. And I think Google was one of the pioneers in that, right? And so that's why it's kind of worth discussing this first commercial paper in some sense. And if you look at the architecture itself, it kind of borrows a lot of the concepts that we have seen that we had seen in academic papers. And what is really insightful about the paper is kind of Google's perspective on this whole problem, right? So I think that's kind of what I want to spend more time discussing, right? So back in the early days of 2015, they realized that they were spending on all these GPUs and doing all this training, and they did some analysis to show that it was actually worthwhile for them to design a chip, invest in what it takes to design a chip in-house, and that would give them much higher performance than the GPUs of the time and consume less power, right? Obviously GPUs are designed for something else, right? They're designed for graphics. They have, branch predictors, they have caches. All of that also gives them unpredictability in terms of performance, right? And if you're in a Google data center servicing queries, you also care about what is called tail latency, right? That is, how long did the slowest responses take? And you want to bring that down as well, right? And the GPUs, because they have these extra microarchitectural features that cause variance in latencies, they wanted to go with something that was much more deterministic, that was customized for the regular computation that you see in deep networks, right? So that was kind of some of their motivation for doing this. And their first attempt, they basically said, let's just do something really quick. Let's just have a basic design. Let's just produce something as quickly as possible. And so within 15 months, they had a chip that they could actually deploy in their data centers. So in the summer of 2016, they had actually deployed these Google TPUs in their data center, and they were able to kind of take measurements on that. Okay, and this first version was only focused on inference. So this one was just for inference, and then they came up with version 2 and version 3, which were focused more on training, right? And version 3 is just kind of like a beefier version of version 2. Okay, and I'll discuss more of version 2 on Wednesday, but I will show you a slide shortly that shows the main differences between version 1 and version 2. Okay, and so here is version 1, 2, and 3. Sorry for the really terrible handwriting. This is version 1. Okay, and sorry, this is also 3. This is version 2, I believe. Okay. So let's look at what they did, right? So they're basically saying that instead of having a GPU card, let's instead have a TPU card. And so this is what the TPU card looks like. It has, this is the TPU accelerator on it. Here are the DRAM chips, the memory subsystem, right? And so that's kind of all it has, right? And you're basically going to send out a task to the TPU, and then the response comes back. And what they essentially showed that this is 15x faster than a GPU. Okay, and so here are some of the other interesting insights from their analysis. So based on the deployment of this TPU in Google data centers in the summer of 2016, they basically realized that 95% of the time you are running either LSTMs or MLPs, right? So based on our earlier discussion, MLP is the multi-layer perceptron, which is a few fully connected layers. And then CNNs, of course, are the convolutional filters, usually used for images where you have a bunch of convolutional layers followed at the very end by fully connected layers, right? And we've seen like the key differences between these two, right? The convolutional layers have few weights, and they have high computations, right? So it's only 25 weights, but you have to do the computations with those 25 weights for every single position in the input feature map, right? So there's lots of computations with a few weights. The fully connected layers have relatively few computations, but a very large number of weights, right? Because every multiplication involves a unique weight. There's no weight sharing in a fully connected layer, right? Whereas convolutions, because of weight sharing, you can bring in a weight and then do a whole bunch of computations using those weights, right? But a fully connected layer has completely opposite behavior, where the computations are few, but the number of weights that you have to fetch is extremely high, right? And that's kind of what is indicated by this over here. The number of operations that you can do every time that you fetch a weight from memory, right? So in the convolutional workloads, you can see that every time you bring in a weight, that can support thousands of operations. In an MLP, every time you fetch a weight, it can only support one computation, right? So truly speaking, this should be one over here. This should be one. These should all be one. Okay, and I'll explain shortly why these are not one, why they are higher than one, right? But I'll get to that in a second. But essentially, there's a difference in these two workloads. And what we are seeing here is that 95% of the workloads fall in that first category, where they're all either MLP or language models. And the convolutional layers are much lower, right? And this was very revealing when this was published in 2017, because all the papers at the time were focusing on these convolutional filters. And part of the reason is it's easier to optimize these convolutional workloads, right? Because you can do things like reuse, like every time you get in a weight, there are ways to reuse that weight. And so that's one way of improving efficiency. And so a lot of the architecture papers were trying to improve efficiency in that way, right? And so this was revealing in the sense that it was a reminder to all of us that we can't just be focusing on convolutional networks. We need to also focus on these fully connected networks as well. Okay, now you can argue that this may have been the case in the summer of 2016. Moving forward, maybe there's a lot more image processing happening, right? So once we get to self-driving cars and so on, you can make the case that more accelerators will be analyzing images and videos than doing language analysis, right? So this number can change over time, but it's it's good to know that this number is very high as well, and cannot be ignored. Okay, now let's kind of explain these numbers over here. Now, if I'm taking the trouble of bringing in a weight from memory and I'm using that weight to do just one computation, that's not very efficient, right? This means I'm going to spend all of my time and energy getting stuff from memory, right? So one way to overcome that problem is to use what is called batching, which says that, don't just work on one image at a time, let's work on 200 images at a time, right? So there are 200 images being processed in parallel, going through one layer to the next. And so when you bring in a weight, I use it not only to do the classification of that first image, I also use it to do the classification of all the other 199 images as well. right? And so that's one of the key features of the TPU, which means it frequently uses a large batch size. And so every time, and if you're working with a batch size of 200, it means that once you fetch a weight, it is used for 200 different computations, right? So you'll see over here that it's the batch size that allows you to kind of increase the number of computations per weight. Okay, and so this is kind of key in trying to understand the performance being provided by the Google TPU. Okay. All right, so let's look at, so maybe I'll explain that a little bit more before I move on, right? So let's maybe talk about this curve, since I'm talking about, fetching of weights and so on. So this is referred to as a Roofline model, which helps us understand the performance of the Google TPU. So on the x-axis, you have the operations per byte being fetched, right? And so, for a fully connected layer, it's going to be right here. It's going to have, one operation for every weight that I fetch. Like we saw in that earlier table, if you're doing convolutional filters, they're kind of in this range, right? There are about 2,000 operations for every weight that I fetch. So these two benchmarks are my convolutional filters, right? So these are my CNNs. So the convolutional workloads are kind of over here, where they're doing 2,000 operations for every byte that I fetch. The fully connected networks, these four over here, are in this space over here, right? Based on the batching that I do, right? I think the numbers were like between 64 and 200. So that's the number of computations that I do every time I fetch a weight. Okay, and this line over here tells me the maximum performance I can expect. Okay, what this means is if every time I fetch something from memory, if I can only do one computation, then I'm really limited by memory bandwidth, right? So the memory bandwidth puts a ceiling on how much performance I can get. The number of computational units that I have puts another cap on the performance I can get, right? And if the workload is memory bound, that means every time I get something from memory, I can only do one computation. Then that puts a limit. The memory bandwidth tells me how many operations I can do per second, right? And so it's a very small number of computations. But if every operation I fetch, or every byte I fetch, I can do 2 computations, the performance would double, right? For every byte I fetch, if I can do 10 computations, performance goes up by 10x, right? And so similarly, if for every byte I fetch, I can do 200 computations, I can get this high level of performance over here, right? So that's kind of what this Roofline model shows. It shows that when you're memory bound, the number of computations that you can do for every byte fetched determines the final throughput, right? This is the y-axis is final throughput in terms of tera operations per second. Okay, and so these are all memory bound workloads. And depending on how memory bound I am, I can see higher or lower throughput. And then I ultimately get to the point where I'm doing so many computations that I'm no longer memory bound. So at this point, I'm not memory bound. Now I'm limited by how many multipliers I have on the chip and whether all those multipliers are busy or not, right? And so in the case of the Google TPU, it has a peak throughput of 92 teraops per second. So once you reach that, you can't get more than that, right? I mean, you're using all your multipliers, you're at peak performance, and so this curve kind of flattens out. And so what they're saying is that for these 2 CNNs that they executed, one of them was able to achieve a peak throughput, or was able to achieve a throughput of 86 teraops per second. So almost as close to optimal. And then there's a second one that was much lower, right? It got only, 1/6 or 1/7 of the peak throughput that it was capable of doing, right? So ideally, if your architecture is well designed and is a good fit for the workloads, you should be pretty close to this roofline line over here, right? It should be pretty as close to this as possible. And so all the MLPs were able to be fairly close to the line here. One of the CNNs kind of fell well short, but this other CNN was able to come pretty close. Okay, does that help? I hope that kind of makes things clear in terms of the workload requirements and how the architecture is perhaps a good fit for that. So let me just pause for a second, see if there are questions that I can answer right now. So somebody asked, what are those tubes? And so it turns out that that's actually liquid cooling in the TPU version 3, actually. So those tubes are what they need to actually keep the chip cool. So somebody asked about the memory bandwidth being the bottleneck. So this is the memory bandwidth between the TPU and its own memory system. So it's not between TPU and CPU or between, you know, host and GPU and so on. Yeah, so somebody asked, you know, why is CNN1 much lower? You know, why is it only at 14, right? And so I'll soon talk about the architecture of the TPU. And you'll see that, you know, if your network is not properly sized, if it's not a good match for the size of the hardware itself, then a lot of those units end up being underutilized. So that's one of the reasons why CNN1 does not do well, right? I mean, if it had a different shape, if the network had a different shape, it would end up utilizing the units much better. The convolutional operation is indeed compute bound, yes. Okay, and then there are a few other questions which I'll answer shortly as I go through the details of the TPU, right? So we skipped a few slides, so let's kind of go back here, right? So this is what the architecture of the TPU looks like, right? And so this is kind of this is the heart of the chip, I guess, right? This is where all the number crunching happens. And so this is the matrix multiplier unit. And this is organized as what is called a systolic array. Right, and I'm going to spend a lot more time on a systolic array in the next class, but let me just kind of briefly describe what it is, right? And I need to give you a little bit more background before I do that, right? So this is essentially what 256 rows and 256 columns. Each of these dots over here is nothing but a multiply accumulate unit, right? So ultimately what I need to do is a dot product, right? I need to multiply two numbers and then add it to something. And so that's what each one of these 64K units is trying to do. It's basically multiplying two numbers and adding it to a term. Okay, now I have to feed this matrix multiply unit with weights and with the input feature maps. The weights come in from up here. They are actually being fetched from external memory, right? So I had, in the slide, I kind of showed you that, you know, you have DRAM connected to this accelerator. Right, so that's these DRAM chips, about 8 gigabytes of them. And this is the bandwidth. This is the bandwidth that I mentioned in this roofline model over here, right? So that memory bandwidth says that, you know, I can't exceed that. And so that's kind of what puts this diagonal line on this roofline model. So if I want that number to be higher, then I need to increase this bandwidth coming in. Okay, but essentially this is how I access the external memory. So the weights are fetched from external memory and are fed in from the top. The input feature maps are stored in this buffer on the chip, right? So this is an SRAM storage buffer. You can see it's really large, 24 MB, right? And from the inputs are basically fed in from the left. Okay, and so basically you have a flow of inputs coming in left to right. You have a flow of weights coming in from top to bottom. And as, you know, two elements meet, they perform a multiplication, they do a certain addition. What comes out at the bottom are the summation of everything that happened in a column. Okay, and so those results come down, they get stored in these accumulators. And then finally, when all the computations for a neuron have completed, the result, you know, goes through an activation function and then it gets placed back in this buffer over here, right? So the output feature map comes back over here. Now, when you're executing the next layer, you know, what used to be the output feature map now becomes the input feature map and feeds in as input again. Okay, so is this general data flow kind of clear? I can go into a little bit more basics shortly, but essentially you're bringing in the weights from off-chip memory. That's expensive. That's why you want to maximize reuse of weights as much as possible. That's why we did things like batching. If you're doing convolutions, there is natural weight reuse, right? Every time you bring in a weight, it gets stored in all of these things over here, right? And so, you know, let's take an example of a kernel, right? So let's take 3 by 3 by 64, right? So to compute this first neuron of my output feature map, I basically need to do 576 multiply accumulate operations. Okay, and so what I'm going to do is I'm going to break it up into multiple stages. I can only have 256 neurons in one column. Right, so what I do is I say, let me first do the first 256 computations over here. So out of these 576 weights, I take 256 of those weights and put them in one column down here. When a certain set of input feature map comes from the left, I do all those computations and the partial sums kind of basically propagate down. Right? The first multiplication takes its result and sends it to the neuron below. You do a multiplication there, add it up, keeps going down. Finally, what comes down over here is a partial sum from 256 multiplications. Is that clear? And at the same time, there's a second filter that I could also apply on the same inputs, right? That also needs 576 computations. I take 256 of those and put them in a different column over here, right? And so since there are 256 columns, I can potentially do 256 filters all in parallel. So once I bring in some activations, they get reused across 256 different kernels, and I produce a whole bunch of partial sums that come down below. They get stored in these accumulators and these buffers down here. In sometime later, I'm going to take the next 256 weights from here, right? So I've basically broken this up into 256 plus 256 plus 64. Right, and so I, having reused all those weights, I then go through another iteration where I look at the next 256 weights. Having done all of those, then I go through another iteration where I look at just 64 weights. And you'll see that in that last phase over here, the utilization has gone down quite dramatically, right? I'm not using all the multipliers at my disposal. I'm only using a quarter of those multipliers. And that's what prevents us from reaching the peak throughput of 92 teraops per second. Okay, so hopefully this example gives you some insight on how weights are being reused, how input activations or input feature maps are being reused. This also gives you some insight on how the computation is broken up into multiple stages. Some stages have very high efficiency, other stages have less efficiency, right? If I didn't have 256 filters, I wouldn't have kept all the columns busy as well, right? So if you're not doing 256 filters, again, your utilization goes down. So you can see that the shape of the network determines how well utilized this Google TPU architecture is as well, right? And that's why we have these different numbers over here, right? The blue line is kind of like the theoretical best, given a certain ops per byte, and then the actual dots tell you how close you can come to that theoretical best based on the shape of your own deep network. Okay, let me again pause here and see if there are any questions. So, so what does it accumulate, right? So like I've just mentioned over here, right? So you're trying to do 576 multiplications and adding up all those results, right? And so in a column, there are 256 different multiplications being performed, and I need to add all those results, right? So the first result kind of comes down, adds itself to the next result. That partial sum goes down one more step, adds itself to the third product, keeps going down. This is how you accumulate 256 sums and then bring it down at the bottom. And then that is stored as a partial sum, saying I'm not yet done with the neuron. Sometime later, I'll produce 256 more products and sums. And so you have to keep doing that. Okay, then the next question is, what is the precision of the Google TPU? It's coming up shortly on the next slide. Does it accumulate the MAC operations or the multiplication operation, right? So in each one of those cells, you're doing one multiplication, and then you're adding it to whatever came to you from the top. And the result of that multiply and add is then sent to the bottom. Okay, so hopefully that answers the question of what exactly is happening with these accumulates. Yeah, and I'll get to the precision shortly. Yeah, so how are LSTMs mapped as well, right? So what I just showed you was a CNN, right? Now let's very briefly talk about a fully connected layer, and LSTMs are nothing but a collection of fully connected layers, right? So it is important to ask, how do I map a fully connected layer over here? So with a fully connected layer, there's not much reuse, right? If I take the trouble of bringing in a weight, I only use it for one multiplication. right? And so it takes a large amount of time for me to kind of populate each one of these different elements, each one of these different cells with a different weight. So that fetch itself takes a large amount of time. And the TPU makes that a little bit more efficient by using what is called double buffering, right? So in each one of these cells, there are two weights being stored. So W1 is the weight that's currently being used, right? And hopefully I'm going to be busy doing all kinds of number crunching for a while. While that is happening, I'm going to start fetching the weight for my next computation. And so that's how I kind of try to stay one step ahead. Okay, and so it takes me a large amount of time to bring in W2 and place it over here. And now if it only contributes to one computation, then I've not given myself enough time to bring in the weights for W3. Right, and so that's where I use batching, and I say that, now that I've brought in weight W1, let me start streaming in 200 different input images, and keep myself busy for the next 200 cycles if possible. Okay, so with a fully connected layer, you spend a lot of time bringing in the weights, and you have to rely on batching to make sure that you're now doing number crunching for a large enough time that you have time to prefetch the weights for the next computation. Okay, so that's kind of how the TPU works, and with a batching factor of 64, 200, and so on, they get a reasonable amount of throughput, but at some point they kind of reach the limit of that roofline model. Okay, so now let's move on to a few more details of the Google TPU, and this should answer the questions that you all had about the precision being used. So GPUs at the time, were only using 16-bit floating point. And so one way that the TPUs beat the GPUs is because they use just 8-bit integer operations. Okay, so people have shown that if you're just doing inference, 8-bit integers is all that you need. In fact, sometimes even less than that. But that's one of the major assumptions that the TPU made. And that's one of the major sources of improvement over the GPU. Right? So one of the main reasons that the TPU does so much better than the GPUs is because they can pack in many more compute units because they're just trying to do 8-bit integer math, right? And this kind of shows you the scaling factor difference in terms of energy efficiency and area as well. Okay, and then like I said earlier, GPUs have features that cause variance. That's another thing that was important to the TPU, right? Where they care about the tail latency for all the queries that they're trying to process. Okay, and then like I just showed you, what I just described is known as a systolic array, right? Where you have flow of operands from left to right, top to bottom. When two operands collide at a certain cell, they do a certain operation there, right? And so this is known as a systolic array. And this maximizes reuse, which says that if you've taken the trouble of getting a weight or taken the trouble of getting an input pixel from some large buffer, let's try to maximize the number of computations that I can do with that operand. Okay, and so again, this is a handy table to kind of keep in mind. It basically tells you the energy difference for different kinds of operations. And so it kind of tells you the benefit you would get if you could somehow go from, let's say 16-bit floating point additions to, let's say 8-bit integer additions and so on. Right, so that's the 13x difference that I had on the previous slide. Okay. So we've covered this, Yeah, so here's the other kind of useful insight that came from this Google paper, right? And so they basically said that, in a Google data center where I'm doing inference on a very large scale, what I care about is response time, and I care about the tail latency for that response time, right? And from various Google engineers who are actually deploying these machine learning models, they first got a constraint saying that I'd like to get my jobs done within 10 milliseconds. And then over time, that number got updated to 7 milliseconds, right? So that was kind of like a magical number for this team, where they essentially had to provide a response within 7 milliseconds. And providing a response within 5 milliseconds is really no big benefit, right? So all they have to do is make sure that even kind of their worst case scenarios are able to meet the 7 millisecond deadline, right? And so they basically, and so some of these workloads can actually finish in less time. And if it finishes in less time, what you can do is you can increase the batching factor, right? So when you do a large batch, it basically says that I'm not just working on one image, I'm working on, let's say 16 images, which means that if I'm doing all of this in parallel, it'll take me longer to produce each individual response, right? So when you do batching, it lowers the individual response rate. Okay, and so what they're trying to do is they're trying to increase batching as long as they stay within the 7 millisecond constraint, right? And so they basically said that for one of their workloads, they were able to go to a batch size of 200 while still meeting the 7 millisecond constraint, right? And with that, they were able to get a maximum, they were able to come within 80% of their peak throughput, right? So this kind of explains why they stopped over here, right? Why did they stop here? Why not do a batching factor that goes more than 200? It's because when they did a batching of more than 200, they were not able to meet that 7 millisecond deadline. And so they had to kind of stop there. And so they were kind of memory bound, and they were not able to reach this maximum throughput of 92 teraops per second. Okay, so I hope that gives you some insight, right? So they're basically saying that, batching is great. It can allow me to get, higher and higher throughput because I'm no longer memory bound at that point. But at some point you have to stop because batching worsens latency. And when you're doing inference, latency is a huge constraint. And so you have to meet whatever deadline has been assigned to you. Okay, so that was a very interesting way of looking at things, and basically says that there's a trade-off between batching, latency, throughput, energy efficiency, memory bandwidth, and so on. So it's a very complicated trade-off that has to be managed. Okay, and so when they finished that work, they basically said that this is something they kind of had to push out in 15 months. And so there are a lot more things that they can do to improve clock speed, all kinds of power down features to reduce energy. You can do more tuning for software. And then they also mentioned that you can add support for sparsity, right? And that's kind of one of the things I mentioned, that building a generation 1 chip, yes, there is quite a bit of engineering and quite a bit of novelty and clever ideas that goes into it. But when you want to go to the next generation chip, that's where the ideas are a little harder to come by, right? So we'll spend a lot of time in the next class looking at sparsity. Okay, and so yeah, so the main take-home messages, they noted that MLPs are important as well. 99th percentile response time is important as well. That has an impact on batching and throughput and energy and so on. And they were able to beat GPUs by a big margin, and most of it was because of being able to do 8-bit integer operations. Okay. Here's the one slide I promised on what the TPU version 2 looks like. And like I said, version 2 is focused more on training. And so, this is a chip that, so when you do training, you firstly need higher precision. And so they actually moved to something that does 16-bit floating point math. In fact, something that they refer to as bfloat 16, which is nothing but the IEEE 754 format, but where the mantissa is truncated to 16 bits. The other key feature over here you'll see is that training needs much higher memory bandwidth. And so you'll see that they've gone away from DDR3 and they now have an HBM interface that gives them much higher memory bandwidth, right? So those are the kind of the two major changes in going from TPU v1 to TPU v2. Okay, so let me again pause for a second, look at questions. Yeah, so somebody just asked, why not use HBM instead of DDR? And you're right, it is because of higher cost. In fact, much higher cost, right? And so you have to be sure that you are memory limited for putting in HBM. And that is the case for training. And we'll talk later about why training needs a lot more memory bandwidth. But for inference, very often just DDR3 is going to be enough. Yeah, so it uses 8-bit integers, and conversion, is it part of the TPU framework? I'm not 100% sure about this. I suspect there is some pre-processing that converts the weights, and I don't, it's not done on the TPU, I believe. I believe you may, I believe the framework probably allows you to convert weights. So they're already in 8-bit integer format, and so you're not kind of burning time and energy at runtime. But I'm not 100% sure about that. So why does training need higher memory bandwidth? I'll save that for maybe Wednesday. But the quick answer is things that you produce in the forward pass, have to be stored in memory and have to be retrieved during the backward pass. And so that's why it needs a lot more memory. Okay, all right, so now let's move on to the next chip that I wanted to discuss. And since I'm running a little out of time, I'll make this a little quicker. And I think it is actually possible because you'll see that the Tesla design looks a lot like the Google TPU design. So, Tesla wanting to do, its self-driving operations on the fly, right? Until April of last year, they were using a card that had GPUs on it, and it worked fairly well, but they realized that they needed to scale up, and so that's when they decided to invest in their own chip, which kind of reduces cost, also gives them higher performance, right? So very similar motivations as the Google TPU. And again, within 18 months, they came up with their first design, and they plan to come out with the next generation 2 years later. And so this is basically something that fits behind the glove box, consumes about 72 watts of power, right? And it kind of explains why you need a custom chip, right? You can't have like a 1,000-watt system that's maybe sitting in your trunk and occupying space there, right? You need something that can kind of fit inside, that fits inside the body of the car. The 72 watts is also important because it determines your driving range, right? So there's a rule of thumb that says that that if you're within 100 watts for your compute system, that has less than a 2% impact on your driving range. Okay, so that's kind of one of their goals. They also care about security and safety, right? So they have kind of features for that because for safety reasons. They have a replicated chip. Every computation is done twice and it's verified, right? And so that way, if there's any kind of fault, right, that's why you're seeing these two chips here. And if there's any kind of fault, it does not give you wrong results. And so the whole system is about 72 watts, reduces cost by about 20% as well. Okay, and so let's just talk a little bit about why it's important to design one of these chips. So if you look at the self-driving car pipeline, there are many different stages, right? And so the three main stages are kind of shown over here. There's object detection, which is trying to find, let's say, pedestrians in front of you. There's an object tracker, which says that if there are cars, where is the car going to be in the next millisecond, right? So you need to not only identify objects, but also predict where they are going to be in the next millisecond, let's say. Then there's a localizer, which says that given all the landmarks around me, can I pinpoint my exact location? And it turns out that these trigonometric calculations based on a map and the image of the landscape, pinpointing your location with these operations is a lot more accurate than using a GPS, right? And so these are kind of like these are the main stages. There's also motion planning, which takes up less compute, but most of the time is spent in these first three stages, and the detector and tracker are the ones that also are dominant contributors. And those two are heavily based on DNNs, right? And we can expect that in the future, if there's ever as each accident happens, I'm sure there's going to be a lot more analysis. There'll probably be better sensors. There'll probably be better cameras. The image resolutions may go up. There'll be a lot more computations being done, right? And so in some sense, at least to me, it seems like the future will require a lot more DNN computations. And so that's why it's important to kind of build these accelerators and continue to scale them up, right? And Tesla makes the same argument as well. Okay, so let me just see if there's any questions about the basics of this workload. Okay. All right, so this is what the Tesla FSD chip looks like, right? And you'll see that the workload is diverse enough that they don't just have to do the DNNs. There's a lot more stuff happening as well, but that's kind of the heart of this chip. So this stuff over here, that's their neural network accelerators. And these neural network accelerators look a lot like the Google TPU, right? So so there are two of them, and each is a 96 by 96 grid of max. Remember that the TPU was 256 by 256. Fed with a 32 MB SRAM, the TPU was 24 MB SRAM, right? So very similar parameters and a very similar design as well, right? This is nothing but, this is again a systolic array. And so that main part kind of looks like the Google TPU. But because the workload is diverse, that chip also has a GPU. It has a 12-core processor over here. Sorry about the colors not being perfect. They have other accelerators over here that do video encoding, image signal processor. So it's a very, very diverse set of accelerators on this one chip. So it's a very impressive case study in that sense. But in terms of neural network accelerators, it's not a huge departure from the Google TPU. Okay, then a whole bunch of other kind of numbers over here, not super relevant. I think we can skip this slide, and you have it for reference if you want to go back to it. Okay, now let's look at a different commercial offering which used a different architecture. And so this is NVIDIA's Volta GPU, which has 640 tensor cores. And so what is a tensor core trying to do? It's basically saying that if you give me 4x4 tensors as input, right? So here's operand A, operand B. Each one is a 4x4 tensor. I'm just basically going to do matrix multiplication and give you the output C, right? And so to produce that result, there are 64 multiplications that need to happen, and then 64 add operations as well. And so what the tensor core tries to do is it basically has the hardware to do all of that, right? So it has 64 multipliers. It has maybe a tree of adders that does those computations. And it basically takes, there are 16 inputs here, there are 16 inputs here. So it takes those 32 inputs and does a broadcast to all of these parallel multipliers. And so in that sense, it's a little different from the Google TPU, which uses the systolic data flow. This one is, I believe, more broadcast based. And so it operates at a smaller scale. We are only operating on 32 inputs at a time, doing all of these operations in parallel, producing that result. And so ultimately, all of your convolutions and fully connected operations have to be decomposed into these 4x4 tensor operations. And then you maximize utilization by keeping these tensor units fed as much as possible. Okay, all right. So then I have a couple of slides on the Intel design as well. There are only a couple of points I kind of want to note over here. You'll see over here that the Intel Nirvana inference engine basically has 12 what are called inference compute engines. And you'll see that there's a large amount of cache on chip, right? So there's 24 MB in a shared cache over here. There is 4 MB in each one of these ICE units. So that's a total of 72 MB buffer storage on chip, right? And this is kind of, this is trying to get, this is close to what we had said earlier was the size of these networks, right? We had said that the modern networks have, between 10 to 100 MB of parameters. So you can see that, now you may not even have to go to memory to get your weights if you can somehow cram everything onto this chip itself, right? The other kind of thing to note is they also use 8-bit integer MAC units. Okay, so I'll kind of skip the NNP training. I'll discuss this more when we get to the training chips, right? And so let me now take a step back, right? So I'm kind of down to my last few minutes. And so I just wanted to end with kind of like a few take-home messages and the common features that we see in all of these designs, right? And so, this is where the number crunching happens, where you can either use a systolic array or you can use a vector MAC unit like you saw with the NVIDIA Volta. Then you have a buffer that feeds in weights. You have a buffer that feeds in activations, right? So in the Google TPU, this was a large 24 MB buffer. In the Google TPU, some of the weights were also stored in the systolic array, right? So this is kind of embedded inside the systolic array, right? But in addition to that, you can also have a separate buffer. And then as you produce partial sums, they get stored in this accumulation buffer, right? So these are kind of like the main pieces in any one of these modern accelerators, right? And so, it seems fairly straightforward. And this is a comment that some of you had made earlier, where these neural network computations are so straightforward, it should be straightforward to design an accelerator as well. And so with these 4 simple rectangles, that's essentially what I've been able to do, right? And there are implementation differences between each of these different chip makers, but they share a lot of these common features as well. Okay, and so ultimately what you're trying to do is you're taking a computation like this and you're trying to map it into hardware that looks like this. Okay, and so this is where data flow comes in. And so since I'm running out of time today, I won't dive any deeper today, but that's kind of the topic for the first half of our discussion for Tuesday's class, where I'm going to talk about data flows and effective data flows, which is taking compute that looks like this and mapping it into structures that look like this, and then trying to figure out, what is the best mapping and what is the best corresponding hardware as well. Okay, so I won't get into this design right now. I'll stop here since I'm hitting the 2-hour mark, and I'll see what questions are already on the Q&A. If you have other questions, please feel free to add to that. And I'll probably go on for the next 15-20 minutes. But otherwise, you're welcome to leave, and I'll see you tomorrow at the same time. All right, so I'll spend some time on the Q&A and try to answer as many questions as I can now. And you're also welcome to add some feedback in the Q&A if you feel I should be doing certain topics that I've not covered. If you'd like to see more details on specific topics, please add that to the Q&A, and I'll try to do it justice in the next 2 lectures. So somebody had a question about how much energy is consumed in the process, and I believe that was a question that pertains to the Google TPU discussion, right? And I didn't spend a lot of time on the final energy numbers, but maybe I can do that right now. Yeah, so this graph over here kind of shows you the total power being consumed. So the Haswell is kind of the Intel CPU host. And what you're doing is you're either plugging an NVIDIA GPU card to that host, or you're plugging in a TPU card into that host. So the host itself, consumes a large amount of power, right? It consumes like 500 watts by itself. And when you plug in a bunch of NVIDIA cards, that takes the power consumption all the way into 1800 watts. If you plug in 4 TPU cards, that takes the power up to 861 watts, where each card has a power, has a max power of 75 watts. Okay, but in practice, it consumes about 40 watts. So you're achieving a peak throughput of 92 teraops per second, while the TPU chip itself is consuming about 40 watts, right? So it is a pretty huge improvement over the GPU state of the art. And one of the reasons for the energy efficiency is, like I said earlier, it's the 8-bit integer operations. It's also the systolic array data flow, which maximizes reuse. So those are some of the reasons for the power consumption being this good. Okay, so someone has asked a question about programming models, and I'm not an expert on this, but I have even undergraduate students that have taken TensorFlow programs and run it on the TPU, on the Google TPU cloud, right? And so I don't believe it's that difficult. I have unfortunately not done the same myself, and that's on my to-do list for the summer. But I believe it's just using TensorFlow, and I think there's a straightforward mapping from TensorFlow onto the Google TPU machines, right? So any of you that actually wants to run something on the TPU cloud, I believe you get a few free hours of compute on the TPU, so it may not be a bad idea to give that a shot. So then there's a question about if the trend is towards more sparsity, does that point to general purpose CPUs becoming more important in the future again? So I think, even with sparsity, I don't think CPUs can compete with some of these accelerators, right? That's like orders of magnitude higher throughput and energy efficiency. So I don't think, I don't think sparsities are going to help much in that in that sense. Of course, modern hardware, or at least accelerators that are available today do not have support for sparsity optimizations. And so, that's something we'll discuss more in tomorrow's class, right? So sparsity is mostly like a research endeavor at this point, but there are a few commercial chips that have said that, we will have support for sparsity, but I don't think we have our hands on that hardware just yet. But I don't think sparsity shifts the dial more in favor of CPUs. I think the accelerators have taken a big lead. I don't think they're going to give up that lead. How about using FPGAs as accelerators? Now, so that's kind of what the Microsoft folks were trying to pioneer, right? So they had a couple of projects. So Brainwave and Catapult are examples from Microsoft. And certainly FPGAs are going to do pretty good. They're going to do better than CPUs. In some cases, they may do better than GPUs as well. And but they're not going to do as well as ASIC accelerators like the TPU. So one of the main arguments that the Microsoft folks had was that some of these algorithms are changing pretty quickly, right? And if the next wave of deep network algorithms use a primitive that is not supported by the TPU, then it's not going to do as well, right? And so you might as well use an FPGA, and within a month or within a couple of months, you can have an accelerator that does much better than the TPU or the GPU. So that's kind of one of the main arguments of the Microsoft teams, that these algorithms are changing fast enough, and they have certain modules that are not amenable to acceleration on the TPU. And so if your workload has that kind of description, then maybe an FPGA would be a better fit, right? So that was their main argument. And I kind of feel that the primitives have stabilized somewhat. So even though algorithms keep changing, right? So like we've seen the efficient net and shuffle net and so on, even though you are seeing these new algorithms, most of their computations are still using the same primitives that you can find on the TPU, right? So in that sense, I kind of feel that the FPGAs may not have much traction beyond these initial experiments. Right now, there may be teams at Microsoft that may give you a very different answer, but those are the trade-offs that are at play. Will you share the slides and videos? Yes, so I think the slides are already online, and I think the videos will be posted, either on YouTube or in some portal that at least the registered folks have access to. So there's a question about transistors for the power supply instead of DRAM. So I think this is referring to my annotations on the figure, and you're probably right. I think I may have mislabeled that figure. The DRAM chips are usually the black chips, and you might be right that there's something else in between that I maybe did not label correctly. So thanks for clarifying that and pointing it out. So I'm not sure what to make of this question. So are there examples of different specialized architectures for CNN and fully connected networks on the same chip? So basically an accelerator that is customized for CNN, and then a different accelerator that is customized for fully connected networks, and putting them both on the same chip. So I don't think commercially there is one that does that today. In research papers, you'll often see a baseline that says, I'm using an iris tile to do the convolutional layers, and I'm using an EIE tile to do the fully connected layers, right? Which is to say that the early layers need to be optimized for convolutions and data flows that make the convolutions energy efficient. And then the later layers need to be optimized for sparsity. And so in research papers, you'll frequently see an accelerator that is a combination of two different styles customized for convolutions versus fully connected. But commercially, I have not seen that yet. But that is actually, once I figured out your question, I think that's a really good good question to pose and discuss. Yeah. Yeah, so another question about programming models, and I'm not an expert on that, so I'm not going to get into that too much. But yeah, there are certain research groups and teams that do focus on how to make the programming process simpler. My operating assumption is that describing a network in TensorFlow and then mapping it to hardware is relatively straightforward, and so that's the extent of my knowledge in the space as well. So I won't be diving much deeper into that. And I think this question about mapping data and weights, right? This has to do with programming models and good compilers. And so if you look at the most recent Grok paper, they spent quite a bit of time on this programming process and what the compiler has to do. So I'm not going to cover a whole lot of it, but this is an area that people do look at very carefully. So sorry to not give you a deeper answer given the time constraints. And another question about GPUs, which I did answer earlier. So I'll jump over this for now. Question about training, which I think I'll do more justice to next time around. Yeah, some resources on systolic array programming. Now, so systolic arrays have been around for a really long time. I have a colleague who, used to make fun of his time in grad school, back in the early 90s, where he would talk about, colleagues who would come up with a systolic array design for like a new workload. That would be their PhD. So, this is a very well-studied topic. And now the workload has kind of stabilized. All we're doing is these dot products, and so the systolic array implementations. We'll cover a few of these in the next class. But the programming aspect itself, again, there are papers, for example, from the Iris team that talk about the programming process. I'm not going to go much deeper into that. I'm going to focus more on the hardware design. But I do believe that, in terms of resources that you're looking for, I think the Iris team at MIT, does have papers that look at the programming process as well. Yeah, there was a question about, are we only talking about CNNs? Are we going to talk about other MLs as well, right? So we are mostly going to focus on convolutional filters and fully connected layers. That makes up most of deep neural networks. I'm not going to talk about things like reinforcement learning or support vector machines and so on. And that's partly because their compute requirements are a lot less. So I'm kind of motivated by publications from Google and others that talk about what where most of the compute is. And so we're going to focus on hardware that's tailored for that kind of compute. Yeah, so systolic array and questions about how the data and weights are mapped. So I am going to cover a little bit of systolic array designs and different examples of data flow, but I'm not going to spend a lot of time on the data and weight mapping process, right? So you do need to understand how the inputs are being fed, right? And so I will cover that, but I'm not going to spend a lot of time on compiler tools to facilitate that data and weight mapping, right? So I will talk about different data flows in Tuesday's class, and I will talk about where the data and weight needs to be so that the computation can happen, but I won't talk about tools to make that happen. So a question about, I guess, the Google TPU and whether the weights are pre-stored in the array. So they are not stored permanently, right? So when you're doing a certain layer, I need to get the weights for that layer. And so there's a prefetch operation that tries to bring in the weights while you're working on the previous computation. Once that computation finishes, you use those weights, and hopefully you're busy for many cycles. While you're busy for many cycles, you start prefetching the next set of weights, right? So they are kind of prefetched, and this is almost a continuous process. So you can't say that they are kind of pre-stored and always available, right? So they are prefetched, and hopefully a few cycles before they are actually required. So there's a question about, is there something that's in between an FPGA and an ASIC, or a combination of an FPGA and ASIC? I have not come across that, which is not to say that it doesn't exist. It might exist, but I've not come across that yet. And if one of you sees it, please do add it to the Q&A or the chat, and I'll look it up. So there's a question about whether there are dynamic things like frequency scaling and DVFS and on-off mechanisms. So I'm not aware of this being part of the TPU. In fact, the TPU paper makes a point of saying that they didn't have time to do all this, right? So they did not even have good clock gating mechanisms. I'm not sure if version 2 and version 3 have more of this, right? So they did put it on their roadmap of things their engineering team would eventually get to, but it's not clear if that's actually a part of the TPU. Yeah, good point about CGRAs. Yeah, I think that's a good way to get to that middle ground between FPGAs and ASICs. Yeah. Yeah, so there's this question about spatial multiplexing of a TPU, right? And let me just kind of explain what I think you mean by that, right? Which is to say that, let's say there are 4 different DNNs I need to run. And the TPU is this monolithic, 256 by 256 grid. So it actually does not have support to do multiple different DNNs at the same time, right? And that's what, and to make that happen, you would need to somehow take that systolic array and partition it into 4 different units, each running a different DNN, right? And so I don't think that support exists in the Google TPU. I did come across Amazon kind of announcing their new chip for this. It's called the Amazon Inferentia, and that does have support for spatial multiplexing, right? And so they kind of break up their compute engine into smaller units. And so, you could have 8 units, and these 8 units could be split across, let's say, three deep networks running at the same time. So the Amazon chip does have support for spatial multiplexing. The Google TPU does not. And again, if there are 100 companies building these chips, and so if they come out with new things that I've not seen, please feel free to add it to the Q&A and the chat, and I'll take a look. Yeah, so question about whether sparsity is handled, and I think I just briefly touched upon this. I don't know of too many accelerators today that can handle sparsity. So the Cerebras folks did say that their chip was going to have support for sparsity, but no details on how it actually does it. So yeah, so apart from these NVIDIA chips, making claims about handling sparsity, I've not seen too much else. Yeah, so good point about embedded FPGAs. I've just not seen too much literature and too many case studies on them. Yeah. And so some of you are kind of answering the question about FPGA plus ASIC option, and I think these are some really helpful links. Thanks. Is it true that most accelerators can be accessed only via PCI Express buses? So at least that, So yes, so when these accelerators are kind of add-ons, that is the case, that they're usually accessed by PCIe. Again, I've not looked at every accelerator out there, and so take that for what it's worth. But the chips that are being designed for training, they are not usually meant as an add-on to another chip. So the TPU V2, and we'll cover some of this architecture, I think, on Wednesday. But it's basically a torus network of a whole bunch of these chips, right? So most of the communication is happening, between these TPUs. So, it is the inter-TPU interconnect that sees most of the traffic. So it's not the PCI Express that ends up being the bottleneck. Yeah, there's this question about CPU, GPU, FPGAs, and the trade-offs. Like I said, the FPGAs are a good fit if you expect your algorithm to be fluid. Otherwise, GPUs and TPU-like accelerators are the best fit. The CPUs, I think, are a distant, 4th place or 5th place in this race. Yeah, and there's this good question about, the ops per weight. I should have answered this question long back, but it kind of got buried in this list. And the ops per weight are indeed affected by the depth-wise and the point-wise convolutions that we looked at. And yes, it may impact the ability to meet the peak throughput of that particular accelerator. Yeah, so it reduces the number of computes, but because it reduces the reuse as well, it may have an impact on the peak throughput and the energy efficiency. So that's a really good point. Another question about FPGAs, which I think I already addressed. So there's a question about Esperanto Technologies accelerator based on RISC-V, which I have not looked at. So I do not have an answer to that question. But I'll try to look it up and see if it kind of pertains to some of the other things I'm going to be discussing on Tuesday and Wednesday. So is vision and language the only areas where ANNs are widely used? So I think, that is certainly the 95, 99% of the case. So there's this, right? And there are a few other domains where they're used as well, right? But they don't rise to the same level of compute that images and language rise to, right? So one example would be genomics, right? Where you can look at somebody's DNA sequence and, you can use machine learning to make all kinds of inferences on that, right? But that's a very small fraction of total compute. So unfortunately, vision and language have taken up most of the attention. So I don't know about this question about bias. So so I don't know if this is a question about fairness in machine learning models, and it's an area that I've not looked at carefully, and so I don't know if the bias has any connection to the prejudice in the output results. And so not an expert, maybe somebody else can do a better job in interpreting this particular question on the bias and its impact on the output results. Can I think of a convolutional kernel as a filter in image processing? Intuitively, yes, except that this is learned and not designed by the software developer or engineer, yes. So I think I'm kind of, yeah, I guess I could go on for a couple more minutes, and I think I'm down to my last few questions anyway. Yeah, so we didn't spend a lot of time on strided accesses for the filters. And strides do introduce all kinds of complications, right? And so is it easier in terms of memory accessing? I mean, it reduces the ops per byte. So it may actually have the opposite effect in terms of memory accesses. So yeah, so there's, I mean, there are other complications that are also introduced by stride because they also make the output feature map smaller, right? Which again is a good thing. It reduces the compute in that sense. So a strided access in some sense is similar to doing a convolution and a pooling layer as well. So I wish I had a better answer to this. I need to think a little bit more about what are the other non-trivial effects of having a stride that is not a unit stride. So someone asked a question about capsule neural network acceleration, and I have no idea what that is. So I'll look that up as well. So there are a couple of new terms that you've thrown out at me, and I'm not a machine learning expert, so this is new to me. But I'll look it up and see what I can learn. I feel like somebody has mentioned capsule to me at some point, and I've kind of forgotten what it is. But I'll dig a little deeper there. Yeah, so I did answer this question earlier about where does the neuron model come from. So like I said, it's kind of biologically inspired, and then we've kind of deviated based on the math of stochastic gradient descent. the Intel neural compute stick, Loihi and Nirvana. So this question came much earlier, and I did cover a couple of examples. Loihi is a spiking neural network, or a chip for spiking neural networks. And so we'll talk about that a little bit more on Wednesday. Yeah, so somebody asked a question on whether CPUs and GPUs can give different answers, and I think the answer is yes, because the precisions do vary. And so a CPU may use a 32-bit floating point. Modern GPUs let you do 16-bit floating point. There are other formats as well, and yes, like we've seen with floating point, as you change the precision, you could get different answers. Yeah. So Advait had a question on ways to evaluate safety and security of ML accelerators. And this is something I've not thought very deeply about. So yeah, I don't have a good answer for that. So Advait, if you're giving this more thought, do send me an email and I can cover this to some extent in the next class. But I've really not thought too deeply about both safety and security, right? I mean, with security, when accessing memory, there are certain things that you can do to make your accesses more oblivious. And then there is leakage, so based on your access pattern, one might be able to figure out the network shape, right? So you may not be able to figure out the specific parameters, but you may be able to figure out the specific hyperparameters. And I've not read up on, techniques to somehow hide that. So I don't have a very deep answer to that particular question. Yeah, so there's a question about, at what point can I call something an accelerator? And I would say that, it's the ISA that to a large part determines if I would call it accelerator or not. So, and I don't think there is, there's obviously a gray area in between where a limited ISA could be viewed as general purpose or an accelerator, right? But I would say the size of the ISA in some sense kind of dictates whether I would define it as an accelerator or a general purpose unit. You could also use, so there was a paper from Stanford which talked about, how efficiency is lost as you go from an accelerator to a general purpose chip, right? And basically says that, as you waste energy on instruction fetch and decode and all that, that makes a chip a less of an accelerator and more of a general purpose unit. So you could use even those quantitative metrics to decide if something is more accelerator or more general purpose CPU. I think I'm down to my very last question. Other examples of ML accelerators integrated inside processor chips? And I can't think of any examples offhand. I feel like I've seen an Intel chip example at some point, that basically had a few additional accelerators on chip. We talked about the Tesla example, right? That's the case where you have general purpose processors, accelerators, deep network accelerators, and a GPU. So that would be an example of a commercial chip that has a mix of all of these. So I think I have answered all the questions out there. Thank you to those who stayed till the very end to listen to these answers. And we can use this as a model for next time too. So I can answer a few live questions and I can save the rest for the very end. So hopefully you found that useful. And you can either send me email. My email address is rajeev@cs.utah.edu. So if you have any suggestions for what you want me to cover in the next 2 lectures, do send me an email, because some of the Zoom stuff may not persist once I close the session. So send me an email as well if you can. All right, thanks everyone, and I'll see you tomorrow.